Okay, so continuing, this for most of you read around 5, around 3.4, and about 1.6. Now, in the previous section of the video, I showed you that it made sense according to R equals V over I, that those values would be like that they would be different. I think many of you probably expected those also to read 5, but I hope you can see from this that that can't possibly be the case. But now, why is it like this? So it turns out that both of these rules, which I'm guessing many of you see, that in a parallel circuit the voltages are the same as the battery, and in a series circuit the voltages add up to the battery voltage. So it turns out that both of these are actually consequences of the conservation of energy. Okay, so why is that? Well, to understand that, I want us to remember that voltage is the amount of energy stored electrically per coulomb of charge. And then let's track a coulomb of charge as it moves through from the battery, where that side of the battery is 0 volts and that's 5 volts. That way we get a 5-volt difference between that point and that point. And let's remember what that means. 5 volts is really 5 joules per coulomb. Now as that charge, which is carrying 5 joules of energy per coulomb, moves through these wires, assuming the wire's resistance is 0, we'll have no transfer of that energy to thermal storage, and so every coulomb of charge all through these wires still carries 5 joules per coulomb. But at this point, we begin to have an area where the resistance is not negligible, not 0. And at that point, we begin to transfer energy from electrical storage to thermal storage through this resistor. Of course, it's got not so much resistance, so we don't transfer as much energy to thermal storage. So over at this spot, the voltage is now 3.4 joules per coulomb. In other words, that coulomb of charge that we are tracking has transferred 1.6 joules from electrical storage to thermal storage, leaving 3.4 joules per coulomb left. In other words, at that spot, 3.4 volts, at here 5 volts, and the difference is 1.6 volts. That's why that reads 1.6 volts. It's a consequence of the law of conservation of energy. Now, in the last part, we have all in here, the voltage has to be 0. That is, all the coulombs of charge that flow there have to carry 0 joules per coulomb of charge. And that is all throughout here because there's no energy loss. If we end up 0 here and there's no energy loss, this also has to be 0 volts. That is, 0 equals 0 joules per coulomb. All right, so if this is 3.4 joules per coulomb and that's 0, then the drop here is 3.4 joules per coulomb, or 3.4 volts. In other words, energy is being conserved here. We start out with 5 joules per coulomb of energy. Some of it's lost here, some of it's lost here, and we end up with 0. Now what the battery does is the battery, by transferring energy from chemical storage, re-energizes that charge, that coulomb of charge, so it again has 5 joules per coulomb, in other words 5 volts, and again as that charge flows through here, it'll lose some of that energy to thermal storage here, transfer more of it even here. So why does it turn out like this? It's a consequence of the law of conservation of energy. The same thing can be seen here. As the charge flows like this, all in the wires here, there's no energy loss. So this is at 5 volts, 5 volts, 5 volts, and all these are at 0 volts because, again, we have to have a 5-volt difference across the battery. And that's your video for today.